In this video, we're going to look at some examples of using Laplace transforms to solve ordinary differential equations. And in this section, we're going to basically be pulling together a lot of different things that we've learned about Laplace transforms earlier in the chapter. There are a lot of examples in the text. In this video, I'm going to be going through some example problems that I'm taking from a handout that you will have in your packet if you have the course pack that I distributed earlier in the semester. There's a 2-page handout. At the top it says use Laplace transforms to solve the given initial value problem. So all the examples in this video are taken from that handout. You might want to try some of those problems on your own before you get too far in these videos. As soon as you're feeling comfortable, we did a few basic problems earlier in the chapter, and the basic idea is pretty much what we've already talked about, but we're going to look at some additional details or complications involving things like the unit step function and convolution. The two main operational properties that we're going to be using are these: the Laplace transform of the derivative and the Laplace transform of the second derivative. Roughly speaking, the Laplace transform turns differentiation into multiplication by s. So it turns a problem normally involving calculus derivatives and integrals into a problem involving algebra. And that's the basic idea of the power of Laplace transforms. So the procedure is going to be the same on all the examples we're going to look at in this video. The first thing we do is take the Laplace transform on both sides of the differential equation. And that gives us an equation for y of s, big Y of s, the Laplace transform of the solution that we're looking for. Usually we'll have to rearrange that to get it into a more convenient form by doing things like partial fractions or completing the square. And once we have that expression for big Y of s in the form that we want, then we invert it term by term to get our solution, y of t, of our initial value problem. So here's problem 2 from that handout. Time derivative of y is f of t, y of 0 is c. Taking the Laplace transform on both sides and using linearity, in other words, Laplace transforming term by term, we get that. Now in this problem we don't know f of t, so we're going to come up with an expression for the solution that will work no matter what f of t is. So we just say that the Laplace transform of f of t is big F of s. So that takes care of the first step in our procedure. We took the Laplace transform on both sides. And the next step, we solve for big Y. We really start solving for big Y. And in the next step, we divide both sides by s. And we're going to be working a lot in this video with convolution and the solution for a lot of these examples. So in getting ready for that, I introduced g of s is 1 over s. And of course, the inverse transform of that is 1, as we learned earlier in this chapter. The convolution theorem says the Laplace transform of a convolution is the product of the Laplace transforms. Equivalently, the inverse transform of a product is a convolution. So when we invert this step, the inverse of c over s is just c, and the inverse of f times g is just a convolution of f and g. And that gives us our solution. Y of t is that integral, then, is a solution of that initial value problem. Another way to think about this is property number 6. in my table. Gives you basically the same thing. So our two basic operational properties are in the orange boxes at the top, the Laplace transform of the first derivative and the Laplace transform of the second derivative. In problem 5, we have another first order DE, but one that contains the unit step function. So we begin by taking the Laplace transform on both sides of the differential equation, Laplace transforming term by term, and using the operational property for the first derivative, we get that. And e to the minus 4s over s is the Laplace transform of the right-hand side. So then we start solving for big Y. We isolate all the terms containing big Y on the left-hand side and move everything else to the right-hand side. Notice we get the characteristic polynomial as expected on the left-hand side. You want to be on the lookout for that. That should always happen if you're doing the calculation correctly. So solving for big Y is 16 over 2s plus 10 plus e to the minus 4s times that rational function of s. And in the first part, I just canceled out the common factor of 2 between the top and the bottom. And in the second part, I called this rational function of s, big F of s, with the idea that I'm going to be using property number 9 in my table to invert that. So I've defined big F of s to be 1 over s times 2s plus 10. You can invert that using either convolution or partial fractions. Here I'm inverting that part by partial fractions in the usual way. And I end up getting 1/10 and minus 1/5 for the coefficients in that partial fractions expansion. So here I took those coefficients, which I now know, and plugged in. And in the second term, I factored out the 2 and the 5. So I actually have a common factor of 10 in both of those. And that's easy to invert. So f of t is 1/10, 1 minus e to the minus 5t by reading our table backwards. So to wrap this up, I had this expression for big Y, and I just found f of t. So now I'm going to use property number 9. The first term here is easy to invert. There's not much more to say about that. But in the second term, I'm using number 9 in my table, which gives me that for that expression for y of t, the solution of my initial value problem. And in the last step, I just plugged in the formula that I found earlier for f of t. So that's my solution of that initial value problem that we started off with here. In problem 6 from the worksheet, we have another first order DE with f as basically anything. We have our two operational properties that we're using all the time here at the top in the orange boxes. We start by taking the Laplace transform of the differential equation term by term. Again, we don't know f of t. F of t can be basically anything. So this solution will allow us to come up with an expression for the solution y of t of that initial value problem that'll work for any right-hand side function, f of t. So the Laplace transform of little f of t is big F of s. So that's what we get when we take the Laplace transform on both sides of the differential equation. And we start solving that for big Y. Collect the terms involving big Y on the left-hand side. Notice again, as we pointed out previously, we get the characteristic polynomial on the left side, and on the right side, just whatever we have here that doesn't involve big Y. In the next step, I just divided both sides by 2s plus 10. So now we have the first term is going to be easy to invert, and then for the second term, we're just going to use convolution to invert that. I've defined big G of s to be 1 over 2s plus 10, which is 1/2 of s plus 5. So G of t, inverting that, is 1/2 e to the minus 5t. So now we have big Y in the form that we want, so we're ready to do the inverse Laplace transform. The inverse Laplace transform of the first term is c e to the minus 5t. The inverse Laplace transform of the second term is that convolution. And in the last step, we just wrote out what that convolution would look like, where f is whatever right-hand side function we started off with in the beginning times g, in this case g of tau, e to the minus 5 tau over 2. So that's the solution of the initial value problem that we started off with in the form of an integral. So the idea here is if we know what c is and we know what f is, we can just take those values and plug them into this expression that we came up with, and then we would have, immediately we would have the solution of that initial value problem. In problem 7, we have a second order differential equation and initial value problem with two initial conditions. So the first three terms here come from the Laplace transform of the second derivative using the known value of the initial, both of the initial conditions, and then plus 4 times sy plus 2 by using the operational property for the first derivative. And just like with the rest of these examples, we solve for big Y. We get the characteristic polynomial on the left times big Y. We move everything else to the right-hand side. So we end up with minus 2s plus 1 on the right-hand side. Then we divide through by s squared plus 4s and use partial fractions on that to get that into the form that we want. So multiplying across, we get minus 2s plus 1 is as plus 4 plus bs. Plug in s equals 0 and we get 1 equals 4a, so a is 1/4. Plug in s equals negative 4 and we get negative, let's see, we get 9 is minus 4b, so b is minus 9/4. So taking those values for a and b and plugging in, now we have big Y in the form that's easy to invert term by term. So the solution of that initial value problem is 1/4 times 1 minus 9 e to the minus 4t. In problem 15 from the worksheet, we have this second order differential equation with f being an arbitrary right-hand side function. And we're going to come up with an expression for the solution of this initial value problem that will work for any right-hand side f of t by, again, taking advantage of the convolution theorem. So we start in the usual way by taking the Laplace transform on both sides and use the operational property for the second derivative. A and B are arbitrary constants here. Then we start solving for big Y. We collect the terms that involve big Y on the left and the other terms that don't involve big Y on the right. So big Y then is as plus b over s squared plus 4 plus f of s times g of s, where we've defined g of s to be 1 over s squared plus 4. And we're going to be, of course, doing the convolution in the next step. So we'll go ahead and invert g of s here and get g of t as 1/2 sine of 2t from our table. And then now we're ready to wrap this up. If we break up the first term on the right-hand side, we're going to have a cosine term and a sine term. And so we know those, we can invert those two things from our table. And the inverse of the last term, again, last term is a product of functions, so the inverse of that is a convolution. So that gives us our final answer here, the first two terms, which we found in the previous step, and then just writing out the convolution, we have this expression. So that whole thing then would give us the solution of that initial value problem for any a, any b, any right-hand side function f.